Right. Very good morning to all of you. So I thought that probably there is a small gap between probably the speed how I say and how I expect you to catch up. I think I should now I revise myself last 2-3 days. Then I should have a different approach. Okay, I'll make it very clear before I proceed. So probably maybe you have to really touch and feel this before we continue. So what I'm passing out is a piece of silicon wafer. This silicon wafer is actually has a doping on the surface. Doping means either phosphorus or boron is actually deposited in the silicon wafer. That means first few nanometers of this crystal, sorry not crystal, this wafer has some phosphorus or boron. You might have studied in your second year or first year that when you have these kind of impurities on a silicon, you make it as a P-type or N-type material, yeah? Okay, I am not sure what type it is. It was just in the lab. For sake of understanding, I just brought this. You can see, so it's a typical 4-inch wafer. So all our chip and all these things are made from this wafer. Probably 1,000 of devices can be made from this. And this whitish thing is a half broken wafer of piezoelectric crystal. Basically, if you tap this on the surface, you're actually generating electrical energy now. Yeah. Okay. So one surface is actually polished, another surface is actually rough. Be careful in your touching; it's quite sharp. You can get injuries. And another small device I'm going to show is a device that is made out of this kind of a piezoelectric crystal. That's the bulk acoustic wave. What I was saying the other day. You will see an aluminium electrode on the top, both sides of the crystal, and this is actually used as sensor for many mass loading applications. So this can go around, and also I will make some discussions as it is. So I just pass it from Ashok or someone. Okay, so all of you are there. Some are missing. I don't know. Friday, some are little missing. Tuesday is possible. Okay. I expect the other way because Tuesday is a bit of afternoon. Yeah. Right.
I mean, once you proceed,
oh. So last class I was discussing about the sensor principles. So one of the very key sensing principles. Okay, the slides I have not updated yet. Okay, that means I will do it today. And also I got the points from other students concerned. I'm also thinking of giving more descriptive notes, not just slides. Just bear with me. I'll post it every weekends. Yeah.
It's gone now.
it's gone.
It'll come back.
Yeah.
So one of the principles what I was talking about chemical sensors, then I was more little detailed with the acoustic wave sensors, and where the principle of these kind of sensors is piezoelectric effect. Yeah. So I said that piezoelectric crystals have certain some grains of structures are there in their material, the one what you're seeing, but as a whole we don't see anything. It's just a solid thing. But what is happening inside is when you apply pressure, you produce electricity, or when you apply electricity, you generate voltage. I thought of just demonstrating with a simple drama show here. Like as usual in computer systems, I want some 9 people.
9.
Can you please just make a small demonstration for the whole class?
9 people.
Yes. Okay. Hold on. And the box here. I need some more people. Anas,
Good.
More charges. Please, I need 6. Okay. Oh, you also last time you participated in my drama. Sorry, Baba. Okay. insufficient for your person. Now what happens is, this is, imagine that, you can slightly lift and show what is your charge. So you can see that there is some negative charges. They are negative, one is positive here. Let me also take a positive. Okay, generally what happens is the crystal stays neutral, like we are staying neutral, all are balanced charges, okay? Now, imagine this is a solid block. Somewhere, what happened is somebody pushed us in front. So what I'm doing is, the positive charges come forward, negatives are little going back. Somebody pushed us. So at the front, you can see that the more positive charges are there. That is, somebody has given a pressure. Okay, positive charges came in front. Okay, now what happens is, when you tap with the electrode, you take all these charges and negative charges goes behind. The population of negative charges is more at the back side and positive is in front. Yeah? So you generate electricity by this way. Okay, you got this? That means basically it was neutral always. Okay, we were neutral. We were just balancing. The crystal was not disturbed and it was balancing. The moment the crystal lattice was disturbed, we just go in front and produce electricity. And this thing again works out the same way. If I may imagine that I am an additional charge which is applied from outside, that is now inverse piezoelectric effect. New charge, I am going to stay with him and deform in front when I apply an electric potential. Yeah? Got it? This is the principle of piezoelectricity. Okay? All of you got this? How this happens? So there are charge ions in these crystals. Now regarding the acoustic wave, okay, what he will do, how the waves are produced. This is piezoelectric effect. Now, okay, Irfan should come here. Okay. Positive. One more positive. Okay, I will change as positive. Sorry guys, I'm disturbing you. Just for the sake of the whole class. Okay, you can be a bit away from negative. Now V3 are positive here. Now imagine that SAW electrodes are like this, okay? The acoustic electrode, what I was saying the other day. Imagine we are the first electrode. We all are having positive. Positive potential is applied to the first electrode. This is one electrode. There is another electrode which is of negative. Imagine there is another electrode here which is again a positive voltage supplied. And there is another electrode here which is negative. Got it? Can you imagine the scene? So positive, negative, positive, negative. Now what happens is, when this voltage is applied like this, just now I told you, because of inverse piezoelectric effect, only this part of the crystal deforms. Can we slightly jump up? We got deformation like this. Since these fellows have got negative, can you slightly sit down? Can you see the deformation? A wave kind of thing has happened. What happens is, when you're doing like this, slightly we push the other particle also, because sound waves. One particle hits the other and it will move. Actually, we moved this guy also. So this has moved the other guy. But imagine at the same time here also a deformation has happened. A cumulative effect happens. And the wave just flows like this. Okay? This is the way acoustic waves are produced on the piezoelectric crystals. Okay? Thank you guys. Thank you. Right, so this is how the acoustic waves, the deformation which happen on the surface, they travel as acoustic waves in one direction. Now, these velocities of these waves are always constant because of the substrate material, the velocity. Okay? So, as I said, it's a constant velocity, but what happens is, in between, so I have these kind of two structures. The velocity is constant, and at the same time, the other end I have another electrode. So I'm going to read the waves which have traveled other end in terms of an electrical signal. Now, when there is nothing as disturbing this between these two, then the electrical signal what I will get on the other end will be exactly the same of the waves what is traveling on the surface. It's very proportional. Okay. Now imagine that there is something has been attached, like say a mass loading has occurred. That means some new particles have been sitting on that. So that will actually give a mass loading to the surface, and these waves, the deformation which was happening, will be slower than before because of additional mass. It is exactly like when we are carrying a bag and walking on the walk. When we are carrying a lot of suitcase or bags, we cannot run actually. We can only walk. Yeah? Same thing happens here. So likewise, the presence and absence of any mass loading can be nicely figured out. Not only mass loading, we can also detect any changes in conductivity, viscosity. All this can be detected, and several sensors have been developed, microsensors. The other thing what I was saying was the bulk acoustic wave, the same kind of waves, the one which I have just now have passed to all of you. If you see the crystal, the complete crystal, there is a two sides aluminium, and in the middle is the white crystal. In this case, that white crystal in between is actually moves in a shear mode. A very short video. It's just 2 minutes of time, but I think it's important to watch that. It's more easy than some animations. Just to know how the bulk acoustic wave can detect mass changes. Now this is a humidity sensing. They are doing humidity sensing before, right? Humidity is actually the water molecules in the atmosphere. Yeah. If it is very humid, we're going to have a lot of such water molecules in this room. Okay. If it is very dry, then we don't have that many water molecules. Now let's say we want to detect such changes using this crystal. How it goes. Okay, this is some company has used it. There's quite a lot of electronics, and it's very similar to your it's exactly what I am transferring there. Here there's a gold electrode. So they are coating some sensing medium here. That's what they say polymer coating. So the measure and whichever we wanted to detect. We pass through this. So when there is no disturbance, now we are zooming in the crystal. The crystal actually vibrates like this. We cannot see in our human eye, but we can see through some other equipments. Now say that water molecules are sitting on that. The velocity of this movement will be reduced because of the addition of mass. Now this change in, okay, stop this. This change in the velocity, now we're talking about in terms of this. So this, since it is a piezoelectricity, this velocity is exactly proportional to the frequency of the signal what is generated from the crystal, the electrical signal. So when there is an increase in mass loading, the resonant frequency of the crystal will reduce. Okay, every crystal, the shape what I have sent you is a 5 megahertz crystal. It's going to resonate always in 5 megahertz because that's the shape it is made. That's how the crystal is. Okay, so but when I'm going to add something over it, that 5 megahertz will reduce to 4.9 or 4.8. So that is proportional to the mass loading what has happened on the surface. So it is difficult to measure the velocity change because you need some laser building. But what people do is they do electrical measurement. They make an oscillator circuit to detect these changes. So this formula is a very well established formula for mass loading changes. So where del F is the change in mass, A is the area of the electrode, and these two are constants of the crystals or quartz. These numbers are given here, and F naught is the original frequency of the crystal. So you can see that the change in the frequency, we call this as resonant frequency shift, is exactly proportional to the change in the mass of the surface. So likewise, sensors can be built based on this principle. So that's what I actually wanted to say that area as well. Okay, so let's now proceed to the next one. I hope it's sort of clear. Maybe I also will give more detailed notes for self-study. Okay, that's the video I want to show. Okay, next we move on to the pressure sensing. So I was saying chemical is for chemical gas sensing principles. We saw that. Before that, I also said something about the biosensing, and now we are moving towards physical sensing: pressure, temperature, humidity. These are some very critical physical parameters that needs to be detected in most of the times. Yeah? So one of the earliest micro device was a pressure sensor. In general, these kind of pressure sensors, oh, there is no board. Yeah? I'm going to have serious problem. I didn't notice that. The board is there outside? Okay, I can bring it. So in general, in the pressure sensing, the principle is usually these sensors have a diaphragm. Okay? So these diaphragms are some flexible sheet of, could be a silicon material or any elastic materials. That means when you apply certain load, it actually gets some strain quickly, and when you remove the load or the pressure, it comes back to its original position. Okay, so what happens is when you apply a load, we actually create a force per area on the surface. Force per area is what? Pressure. But when this force per area acts on the elastic surface on a solid, we call it as a stress. Yeah, stresses. Okay, so we create some stress on these surfaces. Okay? Now, this is the idea. So, whenever you apply load, we want an elastic sheet of material which can bend and come back to its original position. So, what they do is, they take a column-like structures and then a constrained surface, a constrained base, that's very, very hard surface, and this also is quite hard, above which is the flexible diaphragm is fabricated. Now, what happens is, when you apply pressure, this is going to bend and this is not going to bend. Any idea how do we, so we can see that the things are changing and it's proportional to the bending action of this film. Now, as an electrical engineer, how do you think we can measure electrically? How can we sense these values electrically? Yeah? Capacitance. So one idea is, you can actually put an electrode beneath this and another electrode here. Now, when you apply load or pressure, when this is going to bend, this is going to bend like this. Or in other words, this electrode is going to move to a new position. So the distance between these two plates changes, which is actually C equal to epsilon A by D, where we can deduct in terms of change in capacitance. Yeah? So, but what we do is, so I'm going to show you 3 ways which uses this kind of diaphragm to measure pressure. So, as I said, this is one of the very early devices. Okay, the first method is using a piezoresistor. Okay, a while ago I was talking about piezoelectric effect or piezoelectricity. Those are piezoelectric materials. Now there is another kind of material which we call it as piezoresistor. In fact, I have actually also circulated that to you. The bigger silicon wafer what you saw is actually can act like a piezoresistor. Now, what is piezoresistor first? Imagine that I have a scotch tape, tape, normal tape, yeah, which we can stick. I am now grinding a lot of copper powder, okay? I have a lot of copper powder and I'm just spreading on this. Okay, a lot of copper powders are settling like this. Some are touching each other, some are not. Okay? Then what I'm doing is, I'm applying a copper tape at the two edges. Have you seen a copper tape? Or imagine I'm soldering, somehow I've soldered the wire to this tape, okay? Using a copper tape. So a lot of copper particles are there. Some are touching each other or some are very close. This tape could be quite elastic, right? There are normal tapes which we stick. Now when I expand this, you can realize that these copper particles can go more farther. Yeah? So when I am going to put this to a multimeter, I will see that the resistance can go more higher. Yes or not? Yeah? Do you believe with me? Now, if the same thing, if I'm going to slightly, compress it, these particles can come more closer and they can even get connection. Some of them can get connected each other. Yeah? So this time what happens to the resistance? Yeah?
Lower.
Resistance?
Smaller.
Decreases. Because the particles come closer to each other. So in one condition, when I stretch that, the resistance can increase. When I'm going to compress this, resistance can decrease. So I can say this, what I applied is the strain. The proportional to strain, I have change in resistance. Do you get this? So piezoresistors are materials, piezoresistive materials or materials that can experience change in resistance for an applied strain. Or even when you apply a stress, you get a strain. So in fact, a change in stress can be measured as change in resistance. Okay, is this point is clear, all of you? All of you are clear about this? Okay. So the first kind of an idea is using this piezoresistor. So in this diaphragm, let's say the diaphragm we are seeing actually as a two-dimensional view, the side view. So if I see from the top, what they do is on the diaphragm, they place 4 such piezoresistors, R1, R2, R3 and R4. Okay, I'm going to talk more detail on piezoresistors a little later because we need some material background before I touch that. So right now what we'll keep in mind is for a change in when this diaphragm is going to bend, these piezoresistors also going to bend. Why? Because they are stuck to it. Yeah? They are bound to it. So when this is going to bend, this also is going to bend. So when these piezoresistors are going to bend, we are going to have a change in resistance. Assume that this R1 and R2, they are actually, okay, let me follow the figure. Let's say the R1 and R3. Let's say the R1 and R3 piezoresistor, because of the deformation, let's say their resistance got increased. And say R2 and R4, because of the application of the pressure or the strain there, got decreased or negative resistance. So what happens is, if I now measure the change in resistance of this, I can actually relate that to the change in pressure. But once again, changing the resistor also, sometimes if the value is so small, if you keep on relying on the simple change in resistance, we may not do a good work. So what people do is, we can convert this change in resistance as a change in electric potential, because measuring electric potential is more easier. Yeah? You agree with me? Yes? So one simple way is directly we can use a potential divider and do it. But what happens is, again, when we use a potential divider, again the accuracy is a trouble. So what people do is, we go for a Wheatstone bridge. Have you heard of this Wheatstone bridge? Yeah. So the Wheatstone bridge, we make a bridge like what we have in the. So we have 4 resistors. Apply an electric potential to this bridge. So we have R3. Just follow that. R1, R2. R4 and R2. If all these potentials, if all these resistors are equal, we say the bridge is balanced, and we have a net potential of this voltage across these 2 points, A and B will be 0. That's what we call as bridge is balanced. So if the bridge is balanced, we don't get anything. Now say a deformation has occurred. The bridge, some of the resistors have got changed. Now the bridge is no more balanced. Yeah, the different the piezo resistors can have some different values of resistance values. So that creates an imbalance there, and which the voltage across this A and B was 0. Now it's no more balance. No more it is 0. So now if I want to derive a formula for this, what I need to do is this V0 is actually difference between VA minus VB. So basically, I wanted to identify what is the value for VA. So VA can be identified if you just look into this part alone. So that's going to be so let's say this is V in. That's going to be V in into R3. V in into R3 is the same potential divider I'm using. Then sum of both the resistors, R2 plus R3. Similar way, VB would be V in into R1 divided by R1 plus R4. So the sum of all these things, the difference of VA minus VB could be, like the one what has been derived here. That's how it comes there. Okay. So based upon now you can see that the change in pressure or the applied pressure is actually now measured in terms of voltage. Okay. So quite easier. You understand this concept? You understand the concept? Okay. Let me know the engineer's thought. What could be the main problem, do you think, in this measurement or in this type of sensor itself? Have I written that? That's why you should not release the slides anymore before. It's good to have it.
Is there anything to do with the formula?
No, it's not with the formula.
Yes.
It's just electrical concepts.
So what if we press the thing and all of them are the same?
All of them are same. Let's assume that never happens.
The electrostatic system.
No. Very simple. Extremely simple. How many of you are final years now? Who are going to be engineers very soon? Most of you. That's your final semesters. Anyone? Okay. What are the
Noise.
no? Let's always think simple. What are the reasons the resistance can change? Ohm's law. Yeah? Heat, temperature. If you see the Ohm's law, V equal to IR at a constant temperature. That's the formula actually. Yeah. So if the temperature changes, you will have trouble. Okay? We cannot rely much. So if this is some limitations is there. So when pressure changes, pressure is PV equal to nRT. So there is some relationship between these two as well. So quite complexity occurs there. That's one point. Second one, any other idea? The way it is measured? Voltage. Voltage measurement is good, easy to measure. But what happens is, as Ashok was saying, noises. Sometimes the change in the voltages for an applied one, even it could be a noise. It may not be really from this. So voltage measurement is always has a trouble. Okay, let's keep this in mind. So the picture here actually shows the, probably you can see that in your slides. It's a typical how a fabrication is done or the layers is explained here. That's just for illustration purpose, but as a principle we need to know this. So moving on towards the next part is, as I said, a change in resistance could be a trouble with temperature, right? So why don't we see some other thing like the change in capacitance? So that's an idea. Okay, all of them, if this were change in capacitors. So if these all resistors are capacitors. Okay, so let's say this is become C3, this becomes C2, this is C4, this is C1. That means I fabricate, instead of putting a piezoresistor, I follow the one what I told you in the very beginning. Two parallel plates, we apply pressure, the change in the distance between these two actually gives the change in capacitance. Now, if you see the formula of capacitance, the relative permittivity or permitted vacuum, they don't change. They are constants. Okay? So if any change has to happen, should be because of the distance between these two. Now, the overlap area, that's what they say, the area of the, that means in this picture, we have one electrode like this, and there is another electrode like this, but the overlap area is actually this much. The bottom electrode looks to be a little bigger, but the overlap area we only consider the smaller one. Okay, so that area is also going to be constant. It's actually fabricated, it's fixed. So the applied pressure is only proportional to the gap, and it's good. We are going to measure the change in capacitance. So can we use the same circuit? That's good. That's also one way to measure. That's good. So what he's trying to say is, I will use this capacitor as an element in an oscillating circuit. For example, if you can recollect the RC phase shift oscillator, he will say that we'll connect this pressure in terms of a capacitor. I will put this pressure sensor. Then he will measure the change in terms of frequency. Excellent idea. Very good. But my question now is, can we use this circuit still? We can use. That means I should have 4 such pressure sensors, and all the 4 of them I'm going to test, or I'm going to keep 3 dummy capacitors, and one is going to change. Yeah, one of them is changing the capacitor, other 3 are fixed. Okay, or that means initially if there is no pressure, I know what is the capacitance. Those things I choose for C2, C4, and C1, and C3 is the one which is changing, which is my pressure sensor. So what is the change in the derivation I should do now? I'm not going to derive. I'm going to leave it to you. If you don't get the answer, then I'll derive. Eh? Can we change R equal to C? How many of you say we change R equal to C? Okay, first of all, are you with me? All of you are with me? Okay. Are you with me? Okay. If I want to derive the equation for this, can I simply change in this expression VAVB, can I just change R3 to C3 straight away, or I have to do something else? Huh? 1 over C, right? 1 over C. Okay? So you put R equal to 1 over C3, R equal to 1 over C2. Okay? Then probably you will end up with a small expression, and if you solve it, you should actually get this equation. Now this equation, what you see is, as I said in the beginning, the pressure sensor, the capacitive pressure sensor, I know what is the capacitance without the pressure. So what I do is, I now fix all other 3 with the same capacitance, C. Okay? Now only one fellow is changing now, variable capacitor. Now the change in the variable capacitance, say, let's say it is del C. Del C, it's a small increment in capacitance or decrease in capacitance. So you will end up with an expression. If you solve the same way, I'll leave it to you. I will also ask in examination for sure. Many will not do. That's a different story. Okay? That means you should try in your home. Solving this. So in that case, the V0 will be del C by 2 into 2C del C by V. Okay? You get this? What we should do? Yes, you try in your home. If you don't get it, then anyway I'll post the notes later on. But please try before I see my answer. Okay? The thing is, you change the R to 1 by C. Okay? And all the values are same now. Then, again, the change in capacitance is proportional to voltage. Now, an experiment was done by somebody, and they found that if the x-axis, what you see is the gap dimension, okay, and y-axis is the change in capacitance. Is this curve a linear? This curve is not a linear, right? It's a non-linear curve. That means linear means we should have a straight line. So for different applied pressure, I actually end up with a bit of parabolic, yeah, non-linear one, right? All of you agree with this? It's a non-linear. So generally, when we do sensors, when we have a non-linear measurements, it's a bit difficult to complete the instrumentation, because for some values here, up to 1 micrometer here, up to 1 micrometer of difference, that is for up to some values of pressure, it looks linear. Or from 1 micrometer to 2 micrometer, it looks linear for that range. But together it's not linear, yeah? It's a curve. Okay? So there's a non-linear behavior is there because of the capacitance. So the good thing is it could be, it solves a very big issue of using this in elevated temperature. Okay, because the resistors are not used, it's a change in capacitance, so temperature effects are not there. But we end up with another issue now, which is a non-linearity. Also, manufacturing this could be little bulky. Okay, you need to have any guesses how they will manufacture this? Anybody? Between two plates, there is a gap, is there? Any idea? Anybody? Huh?
Dielectric.
Dielectric. Say that's a vacant air should be there. Then how? It's actually a little complicated. So this kind of structure fabrication is complicated. Let me give an analogy. I don't know how many of you have experienced, because all these days, maybe you also might experience. Maybe the recent kids will not experience this. When we go to the beach shores, we used to play like this. We keep our hand in the sand, and then we take other guy will put a lot of wet sand, and he will cover my hand fully. Okay, then I will remove my hand. You will see a small igloo type thing we do, a small building type we can do, right? So what happened is I remove my hand, a hollow thing happens there, yeah? So in this case also, if you see there is a hollow structure, right? So what they have to do is, they have to build this and they have to do some etching to remove the middle part. That's actually quite complicated. So sometimes they don't form a hollow type. Even in our sand experiment, I told you, when I remove, sometimes the thing can just fall down because it's not that strong enough, yeah? So same thing can happen here. So it's slightly complicated to fabricate, but good enough to do some applications. The last slide is somewhat of my inspiration for my overall research as well, is resonant structures. So same thing here, there is a diaphragm, again a similar structure. The first case was a change in resistance, second case was change in capacitance. Now the third case, what they do is, I'm just going to zoom the topmost part. So what they have is, they have a very thin membrane and a small cavity, and there is a small electrode kept over it. So let's say this one is a thin membrane. There's a gap. This thing, the whole thing is attached to some other strong substrate. Now this is like I'm tying a small. I'm tying a thread. I'm tightening it 2 screws. It's very stretched and tight. It's like a guitar string, you know. Then I just oscillate it. It just produces sound. Yeah, right. So it's something like it's the well stretched one. So what they do here is, before applying the pressure which to be detected, they give an AC electrical signal. Okay. Then what happens? It's something like I just gave a guitar string. So what happens to that string? It vibrates. So this thing also will vibrate. Now when it vibrates, they measure that vibration frequency. What is that? They note down as F, no pressure. Okay, this is no pressure is applied. They just give an alternating signal and they measure the frequency. Next time, what they do, they apply the pressure now. Because of application of pressure, this string or this particular diaphragm could be more tightened or loosened. In other words, I will say the fundamental frequency of this thin film has got changed. Okay, on application of pressure. Now, what they will do is they will start sending new. So I'm having a signal generator. I'm actually operating it. First time without applying pressure, I know what is this, so I apply the same pressure and I see it's vibrating. I allow it to vibrate. Then next time I'm measuring the frequency what I have supplied. It was F no pressure. Next time what I'm doing, I'm now sending the measure and what I should do. Now what happens is it's not vibrating like last time because the structure got changed because of the pressure application. I now start tuning this frequency. Okay, slowly I'm tuning. I again get the same amplitude of vibration. I note down this as F with pressure. Say last time this was 1 kilohertz, this can become 1.2 kilohertz after application of the pressure. Now these two difference gives the resonance shift which is proportional to the pressure applied. Okay, so like this. Where's the graph? Okay, there's a graph is there. Okay, so what they have observed is in this kind of devices. In fact, even we have seen in our experiments for certain range of pressures, some certain kilopascal to some, there is a very linear the shift in frequency. This shift in frequency is actually linear for an applied pressure, and it's too easy to measure. Okay. Now I have just left the advantages as planned. Two advantages. What do you think quickly with this measurement? The thing is, the first one is there is no change in resistance or that means we don't. The temperature effects are again it's not there. Another important thing. You can even keep this for your whole life. What I'm saying, the golden words. When you do some measurements. When you try to see the change in measurement, if you measure in terms of change in frequency, it's always advantageous because we don't add any noises to it. Measuring your frequency is more accurate or trustable rather than measuring a change in voltage. Change in voltages can be always, or a change in current also can be always mixed up with some noises. Okay. So we are doing a change. We are measuring the pressure in terms of shift in frequency, which is very advantageous. Second is what is the second one? Linearity. Yes, linearity is there in this kind of devices for not all range again, probably for most of the range. Disadvantages is actually quite again the fabrication issues. I think there is a slide. Oh, I think it's the one slide is missing. Okay. But in general, major problems in the pressure sensor, probably somebody who wants to do research further can think the gap in this is like the overall packaging. So packaging the normal 2D, the IC chips is quite well known, quite easy. But here it's complicated because you have too many things to be packed as one particular chip. This packaging is an issue, and protection of this diaphragm also is sensitive, right? It's so thin, can get damaged and so on. And also it's corrosive, adhesive, and in some cases is very problem with the high temperatures. So these are the three methods how one can actually measure the change in pressure. Okay, and right. So next one is temperature measurement. So temperature and pressure, whichever control equipment, automation, anything, anywhere, you need these things. Temperature, pressure, also sometimes humidity, also sometimes some light also to be sensed. These are very important. So I just choose only these two, pressure and temperature. So temperature, so you must be already aware of this thermocouples. So that means Seebeck effect. I think last class I just started. So when I have two materials of, when I have two dissimilar metals, and if I have a common junction, and if that common junction is maintained in particular temperature, a potential is developed across the two wires, or two metal wires. like what is shown in this picture. Okay. Or similar way, it can also be like this: two wires having two different junctions. One is in cold, another is in a reference temperature, and there is another is in hot. Again, you can measure the potential. So this actually depends upon V equal to beta into del T, where beta is a constant for two materials which are combined. So there is a set of some materials which is used. So mechatronics, any ideas of these materials? Any answers? Any materials you have come across? Okay, no. So this is just tables here. So for example, platinum. Okay, some alloys. Basically, constant and is an alloy. Copper and constant and when if these are the two wires, then we can actually the beta value is actually 38.74 at 0 degrees centigrade. Okay, then one can actually measure a range from minus 270 degrees to 400 degrees. And the range of that voltage is, I'm just taking one as example, which is around 6.26 millivolt to 20.87 millivolts. It's not that big, right? It's few millivolts. Yeah, do you understand? It's just few millivolts. What I measure minus 270 degrees. This alloys can give minus 6.26 millivolts. So, but one can actually choose. These are quite well established. It's there for so many years. We need not produce anything new today, but one can think of producing new thermal sensors which do not produce voltage output. Again, my favorite surface acoustic wave can do it actually. Okay. So now, but this one is quite in the macro level also. It's the same. In macro level also, you have thermocouples in the lab. It's made up of the same procedure. But when we come to micro, okay, these wires or these metals need to be made in micro form in the same chip. Now, what do you expect in the change in voltage when we reduce the dimension? So what will be is this millivolt value? Just now we saw like 6 millivolt change for a temperature of some 230 degrees centigrade. Do you think this temperature will go, this value of the voltage potential difference will go up or reduce when we reduce the size? Actually, it will reduce. We may actually end up with very smaller values because probably we are going for a very smaller length. Okay. There are some scaling laws also governing this. So when we go to the micro dimensions, probably the potential what we generate, or even if you take this few millivolts, what we are saying, if I want to amplify this, or I want to get more better results, what do you think we can do?
Increase the size. Increase the dimensions.
We don't want to increase the dimension, we just want to keep small in the same chip. But say we are now ending up with very low voltage outputs for change in temperature. So what we can do to improve this? Okay, the example I'll tell you. If you have a battery of 1.5 volt, now you want 6 volts, what do? Buy 5 more of 1.5 volts, put them in series, yeah. So what we can do is we can also do these thermocouples in micro dimensions, manufacture them more, but you can serially attach them and create a temperature sensor. Okay, something like this. So then we can have this del V is actually n times the beta del T of that. But there is some example here I just want to cite. Real world example already has been made by some researchers. You can have a look on this. So I again stop here for today. So the next, so almost the sensors I have given the basic principles. The next one we'll see actuators. It's going to be very, very interesting. I'm also want to highlight something. 2-3 years ago, I gave a project on this micro actuation. There was one guy who made a micro robot for the mini project of 4808 just with some wires. We call it as shape memory alloys. And the robot moves. I'll demonstrate this next class. Okay. Don't worry about the lecture.